Hi guys, welcome back to the channel. In this lecture, we are going to talk about how to calculate the collapse load in case of plastic analysis. Okay, so we'll directly come to the topic. So in plastic analysis, the basic need is to calculate what is the collapse load for the structure. Okay, so we are having three methods, right? So first one is incremental method. Incremental method. Okay, and the second method is equilibrium method, equilibrium method, or static method, right? Next method is number third is kinematic method. Kinematic method. So every method has its pros and cons, right? So first we will be talking about the incremental method, right? Then we'll talk about the equilibrium method and then kinematic method, right? Kinematic method is basically based on the lower bound theorem, which we have already discussed. And equilibrium method is based on lower bound theorem, and this incremental method is based on upper bound theorem, right? So now, first we will be discussing about what is incremental method and what are the advantages of incremental method, right? So in incremental method, why we are calling it as incremental method? Because we are increasing the loads. Okay, we are increasing the load till the formation of first plastic hinges, and this increment will continue after till the collapse of the structure, right? So we need to increase the load. We need to increase the load. Increase the load till first hinge, and this will continue, till collapse of the structure. Till collapse of the structure. Right? So what is the advantage of increasing this load? So we'll see with one example. So let us suppose if I am having one propped cantilever beam. This is propped at this end, right? And one load is applied W at the center. Let us suppose this is L, this is L, right? So basically we know that the bending moment diagram of this beam will look like this. Okay, so I am assuming that the bending moment is maximum at this point. Okay, it will come maximum at this point. So when the bending moment, when initially the load, let us suppose initial load is W1. Okay, for W1, this structure is in elastic state. Okay, there is no formation of any plastic hinge, right? So when we increase this W1 load to W2, there is formation of one plastic hinge. There is formation of one plastic hinge. Okay, so this hinge will form at this point when this W is W2, right? So you can see that first we are having W load, then we increase it to W1, then to W2, right? Now the formation of the single plastic hinge will not result in the collapse of the structure. So so one more plastic hinge is needed for this collapse of this propped cantilever beam, and that will definitely form under this load. Okay. So to formation of the second plastic hinge, this W2 increases to W3. Okay. So this is the final collapse load. This is our final collapse load. So you can see that we have increased the load from W to W3. So if someone asks you what is the load required for the formation of plastic hinge, for the first plastic hinge, what is the load required? Okay, so you can easily say that this W2 load is required. So this is basically the advantage of this method, that for you can say that for the successive formation of hinges, how much load is required, that we can calculate through this method, right? So now Now let us discuss one problem on this incremental method and the things will get more clear. So we are having, let us suppose, one prop cantilever beam. Okay. So initially the W load is applied at the center. This is W load, right? And this is A, this is B, and this is C. This distance is 3 meter, this distance is 3 meter. And the plastic moment capacity of this beam, of the cross section, of the beam cross section is MP is equals to 90 kilonewton meter. And this is constant. That means this beam is prismatic. Okay. This beam is prismatic. Means its cross section is same. This is the important thing, right? So now you can see that now in this problem we need to calculate what is the load required to form first plastic hinge, and second the load required for collapse. Okay. So if you ask to find how much load is required for this successive hinge formation, successive hinge plastic formation, you will always use this incremental method, right? This is the advantage of this method, you can say that, but it is a little bit laborious method basically, right? So first what we will do in the incremental method is we need to draw the bending moment distribution, right? Due to this W load, how much bending moment is coming at this support A and this point B, right? So now let us assume this W equals to 1 kilonewton. Okay. So I will be plotting bending moment diagram correspond to this 1 kilonewton load. And why we are doing this, we'll see now. Okay. Right. So how to solve this indeterminate structure? Basically, this static indeterminacy of this structure is basically two reactions are here, one reaction at this point. So total number of reactions are 3, equilibrium equation are 2. Summation Fy0 and summation M0. Fx I am not considering, right? So static indeterminacy is basically 1. So we need to have some redundant over here. Okay, taking C as redundant. Right? Now when I am taking C as a redundant, the structure will look like this. Okay. So first we will be using the compatibility equation at this point. This C, that delta X delta C will be 0. Total deflection, or you can say that the net deflection at C will be 0, because this is a roller support, so it is not allowed. The deflection is not allowed in vertical direction. So this delta C vertical will be 0, right? This thing we have already studied in structure analysis. Okay. So now, due to this 1 kilonewton load, what will be the deflection at this point? So under this 1 kilonewton load, the deflection will be, at this point, it will be 1 into L is 3 cube over 3 EI, right? Beam is prismatic, so that's why EI is constant. Okay. Plus, here the theta value is, there is one theta. So at this end, this will be equal to this thing, and this I can calculate 3 into theta. Okay. So what is the value of theta under this point load? It will be 1 into 3 square over 2 EI, and what is the length? L is 3. So this is the total deflection due to this load, and this will be equals to RC into 6 cube over 3 EI, right? This is through the compatibility equation, right? We are taking this vertical deflection at C equals to 0. So if you solve this problem, you will be able to calculate the reaction at C. So this EI will cancel out each other, right? this thing will become 9 plus this is 27 divided by 2. This is equals to 216 RC over my 3, right? So we will be using calculator to calculate the value of this RC. So 9 plus 27 divided by 2. So this is equals to 45 into 3 divided by 216. So RC is coming out to be 5 by 16, right? And if we take the vertical equilibrium, so I can write summation Fy equals to 0. So F over my 16 plus Fa will be equals to, or you can say that Va equals to 1. Okay. So Va will be 1 minus 16 divided by 16. So this value is basically 11 by 16 Va, right? So we know the reaction at this point Va is 11 by 16. Now what we'll do, and the reaction at this C support is basically 5 by 16. Now we will plot the bending moment diagram for this case. Okay. And why we are drawing the bending moment diagram? Because we need to find the critical location where the first plastic hinge will form. Okay, that we will know through the bending moment diagram only. At this point, right? So due to this 5 by 16 load, the bending moment at this point will be 5 by 16 into 3, right? So this value is nothing but 15 by 16. No doubt in that, right? Now, if you calculate the moment at this point, I'm taking the summation m equal to 0 about A. So due to this RC, 5 by 16 into 6, right? Minus 1 into 3. And I'm assuming that the moment acting at A, the direction is anti-clockwise. So this will be plus MA will be equals to 0. Okay. So if you calculate MA from this point, this will be, if you calculate MA from this equation, this will be 5 into 6 divided by 16 minus 3. So MA comes out to be 9 by 8. So moment at this end is 9 by 8, right? This is for the case when the unit load is acting at this point. Remember that thing, right? Now you can see that this 9 by 8 is the most critical one. Why? Because the moment is maximum value of the moment. I'm not bothering about whether it is hogging or sagging. I'm just talking about the maximum magnitude of the moment. So this is basically 9 by 8, right? So the first plastic hinge will form at this A point, and the second plastic hinge will form at this B point. This B point is second critical location. Okay. So we have decided, or we have found that the first plastic hinge is forming at this A. And how we found that? By seeing this bending moment diagram when the unit load is applied at this point, right? Now you can see that the maximum moment capacity this A point can reach. So maximum moment at A, Mmax at A will be MP. It cannot cross this MP value, right? So now you can see that. Now we'll see, due to this 1 kilonewton load, moment generating at this point is 9 by 8. Okay, I'll be using the linear interpolation over here because this structure is in elastic state. Okay, so we are analyzing our structure like this, elastic plastic state. Okay, so we are here. Let us suppose we are here in elastic state. So I can use this relation. So for this unit load, the moment generating at this point is 9 by 8. Okay, so how much load is required to reach this 90 kilonewton meter capacity? Okay. So that will be X. So if you calculate 90 divided by 9 divided by 8. So this will be x equals to 80 kilonewton. So what is this x equals to 80 kilonewton? X equals to 80 kilonewton means this is the prop cantilever beam. So if you are applying an 80 kilonewton load over here, first plastic hinge will form at this point. So this is the point of first plastic hinge. This is the point of first plastic hinge. First plastic hinge. And remember that our structure is in still elastic state and it is not collapsed. And it is not, this is not collapsed, right? This is not collapse. Okay. So you can see that the load required for the first plastic hinge to form is 80 kilonewton load. And how we calculated that thing? By using this linear interpolation. And why we are using that? Because we are why we can use that? Because we are in elastic state, right? Now this thing is done. So one more thing I can say that when this 80 kilonewton load is applied, so the bending moment diagram will look like this. At this point, the moment is 90 kilonewton meter, right? And what will be the moment at this point? That we can also calculate through that linear interpolation. So due to 1 kilonewton, 15 by 16 moment is generating at the center under this load. So due to 80 kilonewton load, how much moment will be there? Now our moment is unknown at this point. We know the load, but our moment is unknown at this point. So that will be 15 into 80 divided by 16. So at this point, the moment is 75. So this value is 75 kilonewton meter. Okay. So this is, now we'll see a very, very important thing. Now you can see that this point, this portion is reached its full capacity. Right? This section can take maximum extra 15 kilonewton moment. Extra 15 kilonewton moment, which means 19 minus 15. 19 minus 75. Maximum capacity is 90. So 75 is already is there after applying the 80 kilonewton load. So maximum it can take 15 kilonewton meter more moment. Okay. So now you can see that if you increase the load, then there is a moment redistribution. The moment will increase at this point, right? So this point cannot take more moment, and this we are doing because our structure is ductile. The structure is ductile. If the structure is not ductile, then you can see that there will be a brittle failure at this point. Brittle failure. Okay, because it will rotate at constant moment. If ductility is not there, this point cannot rotate. Okay, so ductility should be there to take the advantage of plastic analysis, right? So now we know that this portion, this point cannot provide any moment. Okay, so I am taking this point as a simply supported. Okay, and then again I am applying a load of 1 kilonewton meter at this point. This point cannot take any more moment. Okay, so what I did over here is that I converted this fixed support into this roller support. Okay, because it has already reached its maximum moment capacity, so it cannot provide any increasing moment. And that's why I provided one support over here. It can provide it won't restrict any rotation. And same goes here, right? So if you apply the 1 kilonewton load at this point, this is 3, this is 3. So bending moment diagram will look like this, and the value is PL by 4. So 1 into L is 6 by 4. So this will be 1.5 kilonewton meter. Right? So again, we'll use the linear interpolation because we still are in elastic state. Right? So when you are in elastic state, due to 1 kilonewton load, the moment generating at this point is 1.5 kilonewton meter. Right? So to generate the 15 kilonewton moment, how much load is required? So that if you solve this equation, so x will comes out to be 10 kilonewton. Okay. So for this extra load, this beam can take other extra load this beam can take is 10 kilonewton after the first plastic hinge formation. Okay, so extra load after formation of first plastic hinge. Okay, so total load at the collapse will be 90 kilonewton. Okay, so if 90 kilonewton load is there, this beam will collapse. Okay, and this is during the collapse. This diagram is during the collapse, right? Actually there will be some bending at this point. Okay, this moment is I am showing this moment is showing just only for during the collapse. Okay, so this is what you can say that this is the what you can say that this is the total load is basically 90 kilonewton load is required for the formation of for the collapse of this structure, right? Now, if you draw the bending moment diagram at the collapse, this is very important. So, if you draw the bending moment diagram at the collapse, at this point, it is reached to its maximum moment capacity, that is NP, which is equals to 90 kilonewton meter, right? And at this point, this again reached to maximum moment capacity 90 kilonewton meter. Okay, so this is the starting. This is the what you can see at the start of collapse. The collapse is about to take place, right? And we have studied that during the collapse, our three conditions should be satisfied for the actual collapse load. One is equilibrium condition. Second is yield condition, and third is mechanism. Right. So from two hinges are formed, that means mechanism is there. So this condition is satisfied. Yield condition. What about the yield condition? Yield condition. You can see that in this bending moment diagram, anywhere in this beam, the moment is not crossing this MP value. Okay. So the M is always be less than equals to MP. Right. So here it is less than MP. Here it is less than MP. Here it is equals to MP. Here it is less than MP. Okay. So this condition is also satisfied. Now what about the equilibrium condition? So for the equilibrium condition, if you see, so for the equilibrium condition, let us suppose if this is the beam and we are applying a load and the load is applied 90 kilonewton meter, right? So this is 3 meter and this is again 3 meter. Right? So we need to check the equilibrium condition. So at this end, the bending moment diagram, the bending moment is MP. Here, this is the case, and here we are applying the load 90 kN. Right? So here also the moment is basically MP. Okay? So how to find this equilibrium condition? Equilibrium condition we will check. We'll check the vertical equilibrium is there or not. Summation F equals to 0 or not. Right? Due to if you calculate the moment, if you calculate the reaction, if you calculate the moment summation M equals to 0 at this point at A. So I can write RC into 6 minus 90 into 3 plus MP. MP is 90 equals to 0. Okay. So again I can write RC into 6 equals to 270 minus of 90. So from here I can say RC is equals to So I can say RC is equals to 30 kilonewton. Right? So this is the value of the RC. And if you calculate what is the value of what will be the value of RA, So you can again calculate that thing. So RA will be RA into so RA will be RA into 6, taking moment about this point C, RA into 6 is equals to 90 into 3 plus MP. MP is 90, right? So if you calculate this thing, RA will be 27360 divided by 6, this is 60 kilonewton. So total RA plus RB, is basically, what you can say that is basically 90 kilonewton. Okay, so this satisfies our equilibrium condition, right? But we don't have to check that this condition, because in this method, these conditions are automatically satisfied, right? Because we have drawn this bending moment diagram using these equations only, this equilibrium equation only. So that's why there is no need to satisfy this equation basically. But I'll give you a little idea how to check the equilibrium conditions. Okay. So as you can see that for the prop cantilever, this method looks good because it is simple to form. It is simple thing to analyze this structure which has static indeterminacy of 1. Okay. So if you have a structure that static indeterminacy is very high, right? Suppose you are having this structure. Like this you are having structure. And there is one load W applied here. Okay, and this is 2W applied over here. And you need to calculate what will be the collapse of this beam. For that, you need to first analyze the bending moment. You analyze this structure and draw the bending moment distribution. And drawing the bending moment distribution of this structure is little bit tough, right? As you can see that what is the static indeterminacy of this beam? This reaction here is 2, here it is 1, and again here it is 2. So 2, 3, 4, 5, 6. 6 minus of 2, 4. So it is a little bit, it is a laborious work to analyze this, to find the collapse load of this beam using this incremental method. Okay. So if you want to directly find the collapse of this collapse load for the beam, you won't use this method. Okay. So if you only need to find collapse load for the beam, don't use this method. Okay. But if you find how the structure behaves, how the successive hinges are formed, okay, and how much load is required to form the successive hinges, like how much load is required for the first plastic hinge, how much load is required for the second plastic hinge, this method is very helpful. Okay. So this is the first method we have discussed about how to calculate the collapse load in the increment in the plastic analysis. So if you have any doubt regarding this, you can write in the comment section. Okay, guys. So thank you very much.